All right, guys, we're going to graph some exponential functions. As always, when the opportunity comes up to graph something that maybe we don't know how to graph, I always start by just plugging some values in and seeing what pops out. So let's start with a very basic exponential right here, 2 to the x. So I'm going to plot my x and y. Now I usually like to start with 0. What is 2 to the 0? Well, we know what that is. That's 1, okay, not 0. Anything to the 0 power other than 0 is 1. But what about 2 to the first power? Well, that's going to be 2. 2 to the second power, that's going to be 4, and 2 to the third power is going to be 8. Okay, we're just multiplying by 2, multiplying by 2, multiplying by 2. This is going to get real big real fast. All right, what about negatives? Okay, 2 to the negative 1, that's going to be 1/2. 2 to the negative 2 is going to be 1/4. 2 to the negative 3 is going to be 1/8. It's going to get smaller and smaller and smaller. It's going to approach 0, but it's never going to pass 0. It's never going to turn negative, and it's never going to touch 0 either. All right, so how do we graph this? Well, there's pretty much three distinctive features you need to know to draw a good exponential graph. So a lot of graphs, they have this point at 0, 0. They have some time where they touch the origin, at least their parent functions do. Well, you'll notice we don't have that, okay? Because when we put in to the 0 power, it's always going to be 1. And that is not going to change no matter what our base is, because anything to the 0 power is 1. So we're always going to have this point 0, 1, unless we've shifted it somehow, okay? And then we have 1, 2, 2, 4, 3, 8. Okay, this guy is going to shoot off. It's going to grow much faster than our quadratics or our cubics or any of that. If we go the other way, I have negative 1, 1/2, negative 2, 1/4, negative 3, 1/8. Yeah. Okay, so this is going to keep going, and it's going to get closer and closer and closer to 0, which that should sound familiar. That's an asymptote. So get another color right here. So there's going to be this asymptote on the negative side. Now, this is what we call exponential growth, okay? As you multiply by 2, it's going to grow and grow and grow and grow, all right? So there's 2 to the x. So what about 1/2 to the x? So x, y. Again, if I do to the 0th power, I get 1. But what's 1/2 to the 1 power? Well, that's going to be 1/2. 1/2 to the second power is going to be 1/4. To the third power is going to be 1/8. Now you'll notice this is actually getting smaller. When you multiply by something that's smaller than 1, this is actually going to get smaller. We call this exponential decay. So when you have b to the x, if b is greater than 1, that's going to be exponential growth. If b is between 0 and 1, that's going to be exponential decay. So that's what we're going to see here is exponential decay. Negative 1. 1/2 to the negative 1 is 2. Because remember, negative exponents flip these fractions. We get the reciprocal here. All right. So let's see how this looks. As I go forward, remember we're decaying. 1, 1/2, 2, 1/4, 3, 1/8. We're going to get closer and closer to 0 over here. And then on this side, we're going to start taking off -1, 2, -2, 4, -3, 8. And this guy's going to explode upward. Right? But again, we have this asymptote right here. All right. Now, I'm not going to do any more tables here. We're just going to focus on whether something is exponential growth, exponential decay. We're going to focus on if that 0, 1 point is there. We're going to focus on where our asymptote is. So 2/3 to the negative x. Now, there's two ways that you can think of this problem, and each of them are equivalent, okay? So one way that you can kind of think about this problem with this weird negative exponent is you can go, okay, well, what does a negative exponent do? Well, it gives us the reciprocal. So one way of thinking of this is saying, okay, this is 3/2 to the x, okay? And that's pretty simple there because we know kind of how that works. The other way you can think about this is it's the same as 2/3 to the x reflected over the y-axis. Now, you're going to see that those are equivalent, okay? So let's just sketch this real quick. I'm going to use this the first time. So this will have 0, 1 as my point, my starting point. Now, 3/2, is that bigger than 1? Well, yes. I have people all the time that say, oh, exponential decay, that's when it's a fraction. No. Okay, we can have decimals that do it, and we can have fractions that aren't exponential decay. So the key thing to look at is this guy smaller than 1 or bigger than 1? So in this case, it's bigger, so we're going to see growth. Okay, we're going to see 1.5, 9/4, and it's going to explode pretty quick. And then the negative end, again, will go this way, and we have our asymptote at y=0. Okay. So another way of thinking of this is we could have graphed 2/3 to the x, which is exponential decay. So I'm going to graph this guy real quick in orange. So if I take this guy, I reflect it over the y-axis, what do I get? I get this guy. So however you want to think of that, you can, but either way, you're going to wind up with the same graph. So layer right there. You see, if I turn off one of the lights, there we go. You can see it a little better now. So this time, we're doing the same thing, and we are subtracting 5 from our input. Make that a little bigger, so you can, darker, so you can see. We're subtracting 5 from our input. So that means we're going to have to add 5 to our input to get that same outputs we were getting before. Which that means we're going to have to move this guy 5 to the right. The easiest way to do that, in my opinion, is we have this point that we've had, this 0, 1. So I'm going to move this over 5. And now I'm going to have 5, 1. And I'm going to make this kind of the reference point for everything now. Now it's 1/3. Is that growth or decay? That's decay. So got this asymptote right here. And when I go the other way, I'm kind of exploding up. So this is gradually decaying, but it's shifted over 5. All right. Let's take a look at one more. 1.04 to the x plus 7. I want to look at this real quick because I know we haven't done a lot of real life applications here, but I can't talk about exponential growth without talking about debt and borrowing. and interest. So whenever you take out a loan and there's interest involved, it's a little more complicated when you're paying it down. But if you have a loan like a college loan that you don't start paying on for a while, the debt increases exponentially. Now, the good news is, although it's exponential, it's not something like 2 to the x, because it's not doubling every month or doubling every year, but it's still exponential. Because what happens is you've got your debt, which is your 100%, and then each month or each year, you're getting a certain percentage added onto it. So this is 100%, this is like 4%, okay? So let's say your college loan is like 4% APR. Well, it's 1 plus 0.04, it's 100% plus 4%, which is 104%. Every year, your debt is being multiplied by 1.04, which isn't too bad at first, but there's a snowball effect, and it will eventually be exponential. So let's take a look at what this graph would look like. So 1.04. Now, normally we would start here at 0.1, but you'll notice everything has been shifted up 7. So I'm actually going to start at 0.8. Now, is this exponential growth or decay? Well, obviously, I mentioned that it's tied to interest, so it's increasing. But if you look, 1.04 is bigger than 1. Not by much, but it is. So it's going to be a little slower growing, but eventually it will take off like a rocket, which is why you have to be careful with your debt. And of course, the higher your interest is, the quicker that snowball is going to start rolling. So you really want to try to borrow as little as you can, and you want to start paying it off as soon as is reasonable for you to do that. Now, something else to notice, normally our asymptote is at y equals 0. But remember, everything has moved up 7. So this is going to be the line y equals 7. Because this will never get below 0. But even as this gets really close to 0, you're still adding 7. So as we get close to 0 and we add 7, we're still going to be above that line. That's graphing exponential functions. It's not too bad. You can obviously use Desmos to supplement this. But there you go.